Okay, welcome back. Um, Today we're gonna go over the next lesson in this course, which is 1.2, and we'll be dealing with the measurement of segment and angles, right? And if you haven't watched my previous lesson, I highly recommend that you do, so what to expect in this one, right? So again, without wasting any of your time, let's just get right into it. So, measuring segments, right? How do you even measure a segment in the first place, right? What does it mean to even measure? Um, Now, in real life, right, when we measure things, we use specific instruments like rulers, right, or meter sticks. And as far as the units that we use, right, um, it can vary, right? It can be inches, feet, yards, millimeters, and meters, right? But specifically in geometry, right, when you're measuring the length of a segment, right, what you usually do is, let's say, again, I'm going to draw a visual here, right? Let's say if you have a segment AB, right, and you're trying to find you're trying to write down the length of the segment. So let's say they give you that it's 5 centimeters, right? So essentially what you do is you use the endpoints of the segment, right? So in this case, that would be A and B. So then you do AB, and then you set it equal to the length. So here it would be 5 centimeters. So again, in geometry, usually you're given the units that you're dealing with, and all you do is you just set a specific figure length, right? So for example, for a segment, you would just set it equal to a specific number, and in this case, of course, it was 5 centimeters. Now, moving on, right? These next two things that you're going to be seeing here, they're called theorems, right? So what I've highlighted in the first orange section here, right? Um, Now we'll dive more into theorems later on in the course, right? Because they're extremely important for proving um, certain things, right, or certain problems. Are important for proofs, right? So you'll learn like around 100 theorems in this course, but it's good to memorize them, right? Because the more you have it embedded into your head, the easier it will come to you, right? So the first theorem that we're gonna talk about is if two segments are congruent, then they have the same measure, right? In my opinion, that's pretty like self explanatory, right? Because if two segments are congruent, right, which means they're equal, of course they're gonna have like the same length or like the same measure, right? And um, before I talk about what converse is, usually theorems, right, we have this if-then structure. So, right, you have an if, then, we call this a conditional statement. So the part with the if, right, that's like the first clause, right? And then the second part after then is like what it proves, right? So in this case, right, they would have the same measure if two angles would be equal or congruent. The converse is essentially when you take the if and then you flip them around. So now this part would be first, right? So now you would say if two segments have the same measure, then they're congruent, right? And obviously that's also a true statement, right? Because if two things have the same length, of course, they're going to be equal. What you'll learn later on, though, is that not all converses of a theorem are true. Now, another theorem, now this one has to do with a specific concept, which is a midpoint, right? So let's go over what a midpoint unit is. So a midpoint essentially takes a segment, right, and divides it into two equal segments, right? You can think of it as a middle point, right? That's how I first learned the concept. So here, if you have segment AB, right, this entire thing here, um, and they tell you that M is the midpoint, right? So M is the midpoint of AB, which means that these two segments will be equal to each other, right? So segment AM will be congruent to segment NB. That's what you can conclude. So now if you were to convert this into theorem notation, right, simply put, If a point is the midpoint of a segment, then it divides the segment into two congruent segments, right? If it's a midpoint, basically cuts it right in between, cuts it in half, and the remaining segments are going to be equal to each other. And the converse of that statement, I'm not going to read it to you, but again, that's true also, right? Now, that's the more conceptual way of thinking about midpoint, but there's also an algebraic way, right? There's actually a formula for midpoint, and I think the best way to illustrate this is first um, just to give you some arbitrary variables and discuss on what the formula is, and then we're going to apply it later on. So, how do you find the midpoint if 2 points on a coordinate plane, right? Well, let's say you're given this scenario and you have points A and points B, points A and B, right? And the x and y coordinates for you are shown here, right? x1, y1 for A, and then x2, y2 for B. So how would you find the midpoint? Well, given those coordinates for A and B, if you want to find the middle point or the midpoint, all you would do is take the average of each coordinate, right? So for the x part, you would essentially do x1 plus x2 divided by 2, and then for the y part, you do the same thing, right? So this effectively finds like the middle x coordinate, and then this y coordinate is like the middle y coordinate between those 2 points. And visually on a diagram, of course, right? If you had segment AB, M would be the midpoint, and these two would be AM and MB would be congruent segments. Now, again, this is just another scenario where midpoint shows up, right? Let's say you have segment AB and the length is 8 units, right? And they tell you that AM specifically is 4 units long, right? And they also tell you that M is a midpoint. So because M is a midpoint, right, you can assume or you can conclude that AM is going to be congruent to MB, right? Because remember, it divides into two equal segments, and that means if AM equals 4, that MB also equals 4, and essentially the entire segment is going to be double 4, so it's going to be 8, right? 4 plus 4 is 8. So hopefully that made sense. It's a pretty simple concept once you understand how to apply the formula. So moving on from midpoint, right? I think the next thing that makes sense to learn is a distance formula, right? And here we're going to be dealing with how to find the distance between 2 points on the coordinate plane. So if you have, again, similar scenario, if you, let's say you have points A and C, um, A has coordinates x1, y1, and C has x2, y2, right? The distance formula here, right, to find the distance between those 2 points, you do the change in x squared plus the change in y squared, and then you take the square root of all of that, right? And when I say change in x, I refer to like x2 minus x1, and same thing for y. Now you might be wondering, well, where does that formula even come from, right? Um, because usually it's much easier to memorize a formula if you know how to derive it, rather than just simply looking at it and trying to memorize it from there. Um, so I'll discuss that now, right? So we can form a right triangle like this, right, where you have one leg here and you have another leg here, and then the hypotenuse is going to be the distance, right? So now, what is going to be the length of the bottom leg here, the horizontal leg? Well, it's going to be the change in x, right? It's going to be the distance between x2 and x1, right? Because that's going to give you this specific distance here, right? Which is the bottom leg, and then similar thing for the top, but instead you're not going to be doing the change in x, you're going to be doing the change in y. So that's going to give you these, or it's going to give you that distance, right, for the vertical leg of the right triangle. So now what you can cleverly do is use the Pythagorean theorem to find what the distance would be, right? So again, right, if you guys don't remember the Pythagorean theorem, right, it's a squared plus b squared equals c squared, right? In this case, the hypotenuse is going to be the distance. So you have the distance squared and then equals the change in x squared plus the change in y squared. And if you solve for distance, again, you get back to the actual distance formula, right? So once again, that's how we kind of derive and find the distance formula here, right? Now again, another application of this, right? In my opinion, this is actually really simple. Let's say that they give you that the length of the entire segment AB is 10 units, and then they say that the length of CB or segment BC or CB is 8 units long. So to find the length of AC, well, you just subtract them, right? And then you, of course, get 2 units. Again, a pretty simple uh, application of distance. Now, another theorem that you have to know has to do with congruent angles, right? And it's really similar to the segments theorem that we learned about, right? If two segments are congruent, then they have the same measure. In this case, instead of segments, we're dealing with angles. So now, if two angles are congruent, right, they have the same measure. And again, the converse is true, right? Now, there's specific concepts you should know when dealing with angles, right? And the first major one that we're going to learn about is the angle bisector, right? So an angle bisector is essentially this ray that kind of lies exactly between the two rays that form an angle. So it divides an angle, and as a result, right, it um, makes the resulting angles congruent to each other. And if you want a visual, right, let's say you have angle ABC here, right? This entire green angle here, and they tell you that ray BD, right? That's the red thing, is a angle bisector, right? So what you can conclude is that these resulting angles, right, that are divided by the ray are also going to be equal, and that means angles ABD, right? So angles ABD and angles CBD will be congruent to each other. So again, the best way to think about angle bisector, in my opinion, is think of it as a midpoint, but for angles, right? So it does the same thing as a midpoint. It divides a specific figure into two equal figures, um, but it does it with angles, right? And then again, to kind of translate that into theorem notation, right? If a ray is an angle bisector, then it divides the angle into two congruent angles, right? And of course, again, the converse of this statement will be true, right? Now, still staying with the topic of angles, right? There's many types of angles, and you might actually already know some of these. For these specifically, they have to do with the measure of the angle, right, or how big the angle is. So acute angles are between 0 and 90 degrees, right? And again, if you want a visual, right here, that's essentially what an acute angle kind of looks like. Less than 90, more than 0. And for right angles, right, we've discussed this when we were talking about the Pythagorean theorem, right? Remember, this here was a right angle. Um, right angle is 90 degrees, an obtuse angle is in between 90 and 180, and the straight angle is just 180 degrees, right? Again, those are kind of like the different categories separated by the different ranges of measures that they can lie. Um, Moving on from that, we have like types of angles or like relationships for angles, right? So the first thing is adjacent angles, and simply put, adjacent angles are just a fancy term for saying angles that are next to each other, right? So if you see this entire diagram here, right, um, angles one and two, right, simply because they're next to each other, they're going to be adjacent, right? Because if you want to know geometrically, like exactly why, it's because they share the same vortex and ray, right? So again, angle one and angle two here are adjacent simply because they're next to each other. Now, another relationship is vertical angles, right? Again, I think this is also another important topic, um, but vertical angles are always going to be congruent to each other, right? And How I like to think of vertical angles are just angles that are opposite to each other, right? So yeah, like I said here, right? Think of it as angles opposite to each other, right? So in this diagram, right, you see that angles 2 and 4 and angles 1 and 3 are opposite each other. So therefore you can say 2 and 4 are congruent to each other and 1 and 3 are congruent to each other. Make sure you don't say that 1 and 2 are congruent, right? Because those are not vertical angles. Um, Remember opposite. So angles 1 and 3 are congruent and angles 2 and 4 are going to be congruent. And anytime you see two straight angles or like two lines that intersect with each other, you can always assume that the vertical angles will be congruent, right? All you need to prove for vertical angles is that two of these um, lines that are intersecting with each other are straight angles, and you can always assume straight angles from a diagram. And again, don't worry about that. We'll get later into assumptions um, in a future lesson, but you can always assume vertical angles from a diagram. All right, lastly, for angles, right, or types of angles, we have complementary and supplementary angles. And again, simply put, complementary angles are two angles that sum up to 90 degrees or add up to 90 degrees. So in this case, if you're given that this angle here is a right angle, right? Remember 90 degrees. That means angles one and angle one and two adds up to 90, right? So that's the equation form. And then similar thing with supplementary, right? They're just supplementary angles are just two angles that add up to 180, right? Because they add up to a straight angle, right? So again, right? The equation form angle 1 plus angle 2 equals 180, right? So hopefully that's not too difficult to understand, but this next topic will be a bit difficult because it's not really um, common, right? And it's parts of a degree. So what even does that mean, right? Well, let's start thinking about like something you should definitely know about, right? So time, right? As you know, each hour in a day is divided into 60 minutes, right? So 1 hour has 60 minutes, and then 1 minute has 60 seconds, right? So similarly, right, each degree of an angle is divided into 60 minutes, and each minute of an angle is divided into 60 seconds. Now you might be wondering, like, how does an angle even have a minutes and seconds, right? That doesn't really make sense. Well, we use minutes and seconds for angles to kind of specify the exact measurement of the angle, right? Because sometimes in a problem, you might be given like the um, degree notation for a measure of an angle, right? And again, I'll explain what all of this means, but like you might be given something like this, right? And you'll be asked to like convert it to decimal form, and um, you'll be required to know how the conversion works, right? So that's why this is an important topic, is because sometimes they give you a question with degree notation, and you have to convert it into decimal form. So again, right, just to go over the basic units here, right, we have 1 degree equals 60 minutes. And when we indicate minutes, right, these are geometric minutes, right? These are not like the time minutes. So the notation would actually be this instead, right? So that's how we represent our minutes. And of course, 1 minute here would be equal to 60 seconds, and this is how we represent seconds. So let's try an example problem, right? So if you look at this, right, so you're given 10 degrees, right? How do you convert that to a more specific form? Well, you know that 10 degrees is a sum of 9 plus 1, right? And we also learned that 1 degree, remember, if you go back to our unit, we learned that 1 degree is equal to 60 minutes. So we can convert this 1 into 60 minutes, right? We can split that 60 minutes into 59 plus 1, right? Because remember, 59 minutes plus 1 minute equals 60. So 59 plus 1 here would correspond to the 60 uh, in the previous step, right? And finally, right, using the second conversion, right, of course, 1 minute is going to be 60 seconds, right? Remember, 1 minute is 60 seconds. So you can make that conversion too. And essentially, we get that 10 degrees is equal to 9 minutes, 59 minutes, no, 9 degrees, 59 minutes, and 60 seconds. So that's the more specific or exact way of representing our angle. Now, importantly, right, this is actually really important because sometimes you might have to convert from degree notation to decimal, like I mentioned earlier. So if you have, let's say, an angle and it's 20 degrees and 45 minutes, then to convert it to decimal form, again, just use the units, right? So you can leave the 23 basic number, the basic degrees as it is, right? How do you convert 45 minutes to a degree? Well, you know that 1 degree has 60 minutes. So how many degrees will have 45? 45 minutes? Well, you can set up a proportion, right? If you can say that 1 over 60 equals our missing value over 45. And if you cross multiply and you solve, you essentially get that the missing value is 45 over 60 or 0.75. So this becomes 23 degrees plus 0.75, and that gives us 23.75. So that's how we convert our um, degree notation to our decimal notation so we can, continue on doing what the problem asks us to do in decimal form, which is easier to work with. Okay, and the last thing we're going to go over here is how to find the angle between two hands of a clock, right? And this is actually, um, again, I would say it's a pretty rare topic, but again, good to know. So let's just talk about um, the clock itself, right? So again, this is a standard clock here, right? Now you see 12 sections here, right? Because of the 12 numbers. So when I say section, I mean like how many um, how many regions exist that are between 12 and 1, right? Or between two consecutive numbers. So that would be one section, right? Remember, this would be two, this would be three, and so on and so forth. So there are 12 sections in total, right? Now remember that a clock, right, ideally would be a circle, right? And a circle is 360 degrees because it goes around, right, the entire thing. One complete, um, or I guess you could think about it as a revolution, right, or a rotation, right? It starts here and it goes completely around the back. So an entire circle is 360 degrees, and there's 12 sections, right? So that means each section between two consecutive numbers is 30, right? Because if you do 360 divided by 12, you get 30 degrees, right? So the angle between two consecutive numbers would be 30 degrees, and that's exactly what I did here, right? So why is that important to know? Well, how far would the hour hand move in 1 hour, right? If the hour hand goes from 1 to 2, right, or from 2 to 3, 3 to 4, right, and likewise, right, that just means it would move 30 degrees, right? Because each time is going from one number to the next, right? And we already figured that the angle between two numbers is 30 degrees. So the hour hand moves 30 degrees in 1 hour, right? And how far does the hour hand move in 1 minute? Well, to find that out, um, it might seem hard at first, but all you would do is use the previous ratio we just found. So we learned that, or we found that 30 degrees is how much the hour hand moves in 1 hour, right? You know that 1 hour is 60 minutes, right? And remember, this is the time minutes, right? Not the degree minutes. 1 hour is 60 minutes, right? So the hour hand moves 30 degrees in 60 minutes, right? Therefore, if you simplify this, it will move half a degree every minute, right? Because 30 over 60 is 0.5 or one half. So it will move 1/2 degrees, or half of a degree every minute. Now, those are just useful uh, numbers to remember for problems that we're going to dive into right now. And I listed a bunch of problems. You could kind of pause the video and just look at this if you want to like try one, right? But I'm going to go over two of them, right? So let's start with this, right? What is the angle between the hands of a clock at 5:15? So the first step here is you would just draw the hands of a clock at 5:15. So that's what I've done first, right? I've drawn the hands to represent 5:15 here, right? So again, those represent 5:15. Now, how do you find the actual angle between those two hands? How do you find this angle here? Well, the first thing to do is to count how many 30-degree sections you can pass. And what I mean by that is you can go from 3 to 4, right? And that would give you 30 degrees. You can go to 4 to 5. That would give you 30 degrees. You can't do 5 to 6 because uh, this our hand here, right, it doesn't go the entire way. It's not here, right? It's actually less than 30. So you can count two 30-degree sections, and you have this leftover section here, which we're going to discuss how to find later. But again, for now, right, those two sections here already give us 60 degrees, right? So again, the first thing to do is figure out how many 30-degree sections you can make. Now, how do you find this overlapping or missing area here, right? How would you find that area? Well, there's a formulaic way to do this, right? Essentially, what you do is you look at the minutes they give you for, and in this case, it's 15, right? So it's 15 minutes after 5 o'clock. So you take that 15 and you multiply it by 1/2, and you get 7.5. The reason you multiply by 1/2 is because we learned about a specific ratio here, right? Or a specific unit conversion, which is 1/2 degrees. At the hour hand moves 1/2 degrees every minute, right? So because it moves a half a degree every minute, right? After 15 minutes, it would move 7.5 degrees, right? That means if the hour hand started at 5, right, and now it's at 5:15, well, time has been 15 minutes, right, from 5 o'clock to 5:15, and to find the angle that I moved in those 15 minutes, again, you use that ratio, and you get 7.5 degrees. And if you do 1/2 times 15, you get 7.5. So therefore, this x value here is 7.5, right? The leftover value is 7.5. You add those to the original 60, and your final answer will be 67.5 degrees. So that is essentially the entire clock problem, right? To simply put it, first, to draw the hands of the clock. Second, figure out the number of 30-degree sections you can count, right? Add those up together, and then finally find the leftover section and add that to the original to get your final answer. Now, there's a specific problem that I do want to go over because you actually can't use the same process as you use in this one, and I'll explain why. But let's say you're given time 3:35 and you have to find the angle, right? So how would you do that? So again, draw the hands first. So here, of course, I've drawn that already for you. So this is 3:35, right? 3:35. And first things first, count the number of 30-degree sections. So here you can go from 7 to 6, 6 to 5, and 5 to 4, right? And those together are three 30-degree sections, which will give you 90, right? You can't go 4 to 3 because it doesn't cover the entire length. So you have this leftover section here, and we'll just call that x. Now, normally what I told you to do is take the minutes here, right, 35, and multiply it by 1/2, right? But that would actually be wrong in this case. Um, what you would instead want to do is do 60 minus 35 and multiply that by 1/2. The reason is right? And this is a really important distinction to make when you're looking at these problems, right? Is this a specific piece of text here that I've written for you, right? So in the last example, which is this one, right, it may be confusing why you do 60 minus 35 instead of just 35, right, times 1/2. And the reason why you do that is because you have to consider the position of the minute hand relative to the hour hand, right? So what I mean by that is if the hour hand was like if the hour hand to use seems to be in front of the minute hand, then you have to use the minute number itself, right? So for example, right here in the previous problem, right, the hour hand seems to be in front of the minute hand, right? So you go on and just do 15 times 1/2, right? Now in this scenario, right, the minute hand seems to be in front of the hour hand, right? So instead of using the base number 35 itself, you would actually do 60 minus 35 and then divide that by 2, right? So again, once you understand that specific distinction, this becomes much easier, right? So again, in this problem, we have the minute hand is in front of the hour hand, right? So instead of just doing 35 times 1/2, you would do 60 minus 35 times 1/2, and that would give you the leftover portion here for x. So of course, if you figure x out, you get 12.5. You add that to the original 90, and your final answer is 102.5. So that's all for this lesson. Um, in my opinion, the hardest part about this lesson is just these clock problems, and specifically this scenario why you have to do 16 minus 35 or 16 minus the number of minutes. But other than that, um, everything else I've covered, right? Again, this is important to know. Make sure you know the theorems for the upcoming lessons because the theorems build on each other, right? And it's good to start memorizing them now so you don't have to like memorize 100 at a time when we get to the end of this course. But thanks for watching. If you have any questions, leave it in the comments, and I'll see you next time.